This is a continuation of Module 1 Probability Theory Refresher, and this is the lecture 2. So, the lecture 1 we have covered what is the motivation behind the stochastic process. Then we have given a few examples, and followed by that we have explained what are all the minimum things is necessary to study the stochastic process. We started with the random experiment, then events, then the probability space, and to create the probability space we need a sigma algebra. Then after creating the probability space, then we have defined the conditional probability, then we discuss independent of events. Then we have list out a few standard discrete random variable as well as a standard continuous random variable. Even though we have discussed only 3 or 4 discrete and continuous random variable, there are more, but whenever the problem comes we will discuss those standard distributions when we come across those distribution. And the lecture 2 we are going to continue whatever we have discussed in the lecture 1, basically the probability theory refresher. In this we are going to give a brief about what is joint distribution, and if the random variables are independent, what is the behavior of a joint distribution and so on. Then we are going to discuss covariance and correlation coefficients. After that we are going to discuss the conditional distribution, then followed conditional expectation also, and we are going to list out a few generating functions, probability generating function, moment generating function, and also the characteristic function. Then at the end of the probability theory part we are going to discuss how the sequence of random variable converges to some random variable, and for that we are going to discuss the law of large numbers also. And at the end of the lecture 2 we are going to complete with the central limit theorem. So let me start with the joint distribution of random variable. So suppose you have a random variables x1, x2, xn. We say this random variable is a n dimensional random vector. Means each random variable x1, x2, xn are the random variables, either it could be a discrete random variable or continuous random variable, and we are going to make it as a together in the vector form, and each one is going to be a random variable. Then it is called a n dimensional random vector. Once you have a together as a vector form, then we can go for giving the joint distribution. So the joint distribution we can discuss in two ways. Either it is a joint probability mass function, or we can define as a joint probability density function. Suppose you take an example of a two-dimensional random variable x comma y. If both the random variables are discrete, random variable x is discrete as well as the random variable y is discrete, then you can define what is a joint probability mass function of this two-dimensional discrete random variable as probability of x comma y. Here the small x, small y are the variables, and this x comma y denotes the two-dimensional random variable. This is nothing but what is the probability that x takes the value, random variable x takes a value small x, and the random variable y takes the value small y, and based on the possible values of x and y you have the probability of this. That means you will end up creating what is the event which corresponding to x equal to x and y equal to small y. That means if you not getting any possible outcomes that gives some possible values of x comma y, then it may be the empty set. Otherwise you will end up with a different possible you can collect the, that means x is equal to x and y is equal to y. For all possible values of x comma y you may relate with what is the event in which x of w gives the value x as well as y of w gives the value y, where w is belonging to omega. That means you collected a possible outcomes W such that it satisfies both the conditions where W is belonging to omega. That means this is going to be the event, therefore this is the probability of event. And you know, by using the axiomatic definition, the probability of event is always greater than or equal to 0 and the probability of omega is equal to 1. And if you take mutually exclusive events, then the probability of union of events is going to be the summation of probability. Therefore this is the way you can define when the random variables x and y both are discrete type. Then you can give the joint probability mass functions. Therefore here this is the joint probability mass function, and this satisfies all the values are always greater than or equal to 0 for any x and y. And if you make the summation over x as well as summation over y, then that is going to be 1. Therefore it satisfies the property of always greater than or equal to 0 for any x and y, and summation, double summation over x and y is equal to 1. Therefore this is going to be the joint probability mass function corresponding to the discrete type random variable. Suppose the random variable x and y are, each random variable is a continuous type random variable, therefore you will end up with the two-dimensional continuous type random variable or random vector. In that case you can define what is a joint probability density function is of the form f of x comma y small x and small y. That is going to be what is, so you can have a joint probability density function, and you can relate with this joint probability density function with the CDF by what is the CDF of the random variable, that is nothing but what is the integration from minus infinity to x and what is the integration from minus infinity to y. What of the integrand is going to be r comma s, where r is with respect to x, that is dr, and this is ds. That means since you have a continuous type random variable, therefore you may land up with the continuous function with the two variables x comma y. By using the fundamental theorem of algebra, you can always land up a unique integrand, and that is going to be the density function for this two-dimensional continuous random variable. And you can able to write the left hand side continuous function in x and y can be written in the form of integration from minus infinity to x and minus infinity to y of this integrand and ds, whereas this function is going to be called it as a joint probability density function for the random variable x comma y. So there is a relation between a joint probability density function with the CDF. You can I can give a few examples. In the example 1, suppose you have both a random variables as x comma y is a discrete type, then I can give a one simplest example of I comma j, that is going to be 1 divided by 2 power I plus j, for I is belonging to 1, 2 and so on, and j can take the value 1, 2 and so on, and this is going to be the joint probability mass function for two-dimensional continuous type random variable. If you made a summation over x and summation over I and summation over j, then that is going to be 1, and you can get by summing it over only j, you will get the probability mass function for the random variable x. Similarly, if you make the summation over I with the joint probability mass function, then you may get the probability mass function for the random variable y. That means from the joint probability density function, by the joint probability mass function, by summing it over the other random variable, you can get the distribution of the single random variable. Suppose if you have a n dimensional random variable, suppose you for n is equal to 5, you have a 5-dimensional random variable. Suppose all the random variables are of the discrete type, then you may have a you may have the joint probability mass function of this 5-dimensional discrete random variable, and by summing over each random variable and if you want to find out what is the probability mass function for the one random variable, you can always get make the summation over other random variables with respect to the other random variables. You can get what is the probability mass function for, by summing it over the other random variables. You will get the marginal distribution of the random variable x1. Similarly, you can get the marginal distribution of x2 or any other random variable. Similarly, suppose you have a joint probability density function. From that you can get the marginal distribution of one random variable by integrating with the other random variable. By integrating with the other random variable. So this is a joint probability density function. From the joint probability density function, by integrating with the other random variable, you will get the probability density function for this random variable y. Similarly, you can get the probability density function for y is, so you can, by integrating with respect to r, so that means you are just finding out the marginal distribution of the random variable y, and here you are finding the marginal distribution of x.